if you are undecided on what campus you're transferring to and you want to get some information, this would be a good session to attend. So,
Oh, okay.
right.
Actually, I think they did send some emails.
Okay, okay. They send emails and then they tell us to send emails, and I'm like, I feel like when they send an email and there is no expectation of the email is not read. So I've decided to stop sending emails until I talk to you guys about it, at least in the recording. So then you can look forward, forward towards the email
Yeah.
versus just sending the email and there's no introduction. It's just like, bam, there's the email and it seems like spam or something.
Right.
Yeah, but that way you know the purpose of the email, but it's just transfer information. Since everything is being done online, tomorrow will be all day sitting down, which is really hard for me to sit down hours at a time.
Yeah.
But yeah. Okay, this is where we ended. So, but yeah, we're going to be at meetings all day long tomorrow. But it doesn't mean I'm unavailable completely. Officially, I'm unavailable, but really, if you send me email, I can email you back, even if I'm in the meeting. Because some of the sessions are on demand, so I can pause the video, respond to you, and then continue. Okay? Yeah. Okay, so let me pick up where I left off yesterday. And essentially, we talked about regular rate laws, and then now we're looking at integrated rate laws. With the integrated rate laws, let me start with the purpose so that we understand why we're learning this. Because, wait, let me make sure I'm recording. With the regular rate law, what we're trying to do is figure out strategy. How can we get the reaction to go faster, right? With the integrated rate law, what we want to figure out is how much of the reactant is left over at a specific time. So if you're trying to, so the purpose here overall is calculating the amount of reactant left after a specific time has passed. Okay, so when I say purpose, for me, purpose has to be meaningful to my life or your life, right? So why are we learning integrated rate laws? Think about it from a medicinal purpose. If you're taking medications, all medications do not operate in the same order, so to say. Some medications are processed by the body faster. Some medications take a longer time because medications are essentially chemicals. So the scientist who is designing the process by which the medication is made has to be aware of all of this. And they have to figure out how, I mean, it's a little bit more than just chemistry, right? It's chemistry and biology, so biochemistry, they're kind of combined working together. How much of the medication will be left in the system after, say, 6 hours, 4 hours, 2 hours? So depending on how much is left over, they will then tell you take another dose, right? If it's running out, you need more in your body, take another dose. So even deciding how often a person should take a medication boils down to the integrated rate laws, because you want to know how much is left in the system. There are times when, because of biology, things get complicated, just your metabolism is slow, and so maybe it's not really, your body is not processing the medication as fast as expected, then you're not monitoring the time that you're pretty much taking the medication. When that happens, you can have some overdosing issues, unintentional, where you're taking the second dose too close to the first dose. Bottom line, the purpose here is for us to figure out how much of the reactant is left over at a specific time that has passed. So we use this in medicine, we use this in nuclear chemistry and other areas of science, okay? So as we're going into this, we will use the same rate laws, but we're going to use what is called the integrated rate form because it does help us to get more information. As usual, we'll be focusing only on the reactant concentration, not the products, and that will help us to get the information we need. So it says here, when you apply calculus to integrate the rate law that we were using before, it gives us another form of the equation that shows the relationship between the concentration of A, the reactant, and the time of the reaction. This is called the integrated rate law. And once again, we're learning this because of the purpose and the tool it provides us with. So we're starting with zero order like we did before. We'll go over zero order, first order, then second order. So in the zero order form, we said yesterday rate equal K A raised to the power of 0. This is what the zero order looks like. Or rate equal constant K, because A power naught, which is 0, equal 1. So when you integrate both sides of these, take a log natural of both sides and kind of work it out, you get this form here. And this form is the integrated form of the same equation. I'm not going to go into the integration part because calculus is not a prerequisite for this class. If you decide to minor in chemistry and you take physical chemistry, which is the junior level of this class, you will be required then to work this out, because for that junior level chemistry class, calculus 1, 2, and 3 is required for that class. So then you'll be held responsible for this information. So what you need to know, like we covered yesterday, the rate law. So you need to recognize this, or that the first form or the second form. And this is sometimes called the differential rate law, or just the regular rate law. Okay. The second one is called the integrated rate law. That's this one right here. Okay, the integrated rate law. Oh, I like the yellow better. This one. So once again, what does this integrated rate law provide us with? It allows us to compare the initial amount of the concentration of A and the final amount. So let me go ahead and add a page here so I can write things my way. So I'm going to kind of look at this and see what it provides us with. Then not only that, I feel like in analyzing chemists, I feel like there's a preference for chemists. When it comes to graph, based on my journey in chemistry, I feel like chemists prefer linear graphs. So if they can linearize anything, they would. The integrated rate law tends to be in a linear format. So we'll talk about that too. So this equation right here, if you look at, actually, let me label it right here. This represents the initial or starting concentration of A. Okay, and then this one here represents the final concentration of A. Now, when I say final, it's technically really the concentration at a certain time t. So really the word final here is not the correct term. It's just concentration at a certain time t, right? Because the reaction may continue, but that's pretty much it. And then what is t? This is the time that we're talking about, the time that has passed, the one that allows us to have this concentration. So this amount that's left relates to the time, right? So if more time has passed, we have less amount of the reactant left over. And then what is K? K is that rate constant. Okay? So we're able to connect all of these together. Now let's see what else are we seeing here. Now that we see what this provides, remember, we can figure out the amounts as needed. I want to also go ahead and show you what else. Oh, the graphical form. So since we have a linear equation, how do you get a graph from that? So a graph of zero order, A sub t equal negative kt plus A sub naught. Okay, this translates into y equal mx plus b, or c, whatever the last letter is, right? So you can see here, this is a point slope form of the graph. It's linear. Now, based on this, let me try to relate these two. This is going to be your y-axis, right? The concentration of A, the reactant at any point in the experiment, the amount left over. This will be the initial amount, the starting amount. We know it's linear because it matches this format, right? Remember, this is the linear form, linear equation. So this equation we have here is linear. And then let me see. So we got our y and we got our x right here. So if our x is t, then our slope is negative k. Okay? So what I'm going to do here is sketch a graph based on this. So we're seeing here we have a linear graph. The title of this graph will be A concentration of A versus time, right? I'm just going to draw this part here versus this. I have a slope. My slope is negative based on this right here. So I can write, it's a straight line with a negative slope right here. When the line crosses the y-axis, that gives us this value here. So this is going to be A naught. The y-axis is just A in general. The x-axis is T based on what we have here. This is the y-axis. Let's say just that. The x-axis is going to be T. So I put that in there, right? Now I have one more thing to display. My slope, I'll say here, slope is equal to, according to this, my slope is negative K right here. So based on this equation, based on this point slope form, I'm able to sketch a graph that is consistent with this. I don't know the actual numbers. I just know the relationship between the parts in the graph. Okay? So you want to make sure you know how to sketch the graph like I just did. It's a line sloping backwards because of the negative slope. You want to make sure you know from the equation how to label the y and the x-axis. We'll do a bunch of these to where at some point it will become second nature if you don't know how to do it yet. Okay? Okay. The other thing you need to know is the half-life. We talked about this yesterday, but we're going to talk about it again. So for the zero order, the half-life, the way you get the half-life, I'll talk about it, is essentially you take this final amount, which is right here. Let me erase some of this stuff here. You take up the final amount, which is right here, and replace this with the initial amount divided by 2 because it's something called a half-life. So let me go ahead and define that before I have this right here. Let me define what a half-life is. I just feel like sometimes some things are said out of order. I know what it is, and then I have to kind of think about things from your point of view. Half-life is the time it takes. So we're figuring out something called the half-life. Half-life is the time it takes for the original amount of reactant that will be A naught to reach half the amount. Meaning you end up with half of what you started off with, right? So if you started off with 10 molar, now you're left with 5. So the time it takes for the original amount of the reactant you have to reach half that amount. But we need the time it takes for us to go from the original amount to half the amount. How much time is that? Okay. So in our original equation we have, I'm just going to show you how they work this out this one time. We said it was A sub T equal negative K times T plus A sub 0. The 0 here just means the beginning, right? And then the time T is the end. We have no idea what the time is, so we just leave it as T. Okay, so if we want to figure out half-life, so I'll say here, for half-life, what you do is you replace the T. I'll say replace the T with T1/2 because T1/2, this is called half-life. Okay, that's the first thing you do. Second thing you do is your target concentration, the amount that you want to be left over at half-life, should be half of the original. So replace this with A naught over 2. So at the end, oh, I just realized I kind of skipped over this part. I should say replace, right? At half-life, you want to replace this concentration with that. So what happens is you end up with A sub naught over 2 in this position right here equal, the constant is still the same, it's the same reaction. And then at T, you put T1/2 plus A naught. Then you work this out, rearrange the equation, and then this magically works into T1/2 is equal to A naught over 2K. So here's the thing. For this section here, you don't need to know how we got from this to this, but you need to know the half-life equation. So I'll say no. Okay? So how can this question be asked to you? Conceptually, they can say, does the half-life of the zero order depend on the concentration of the reactant? Look at this equation mathematically. Mathematically, T1/2 is a variable, right? A naught is also a variable in this mathematically, right? And so since these are here, since A naught or A concentration sub naught, that's just the initial concentration, is in the equation here, you can just say, just to kind of keep this simple, the concentration of A, as in this number here, and the bottom number, K, influence T1/2. How do I know that? Because they're in the equation. Any symbol not showing up in the equation right now does not influence the half-life. So let me try to write this out conceptually, because that's the part where I feel like most people, oh, hold on a second. Let me tell my coworker I'm in class right now. Oh, she'll get it. Some people think I'm just living that life, right? No, I'm just kidding. I normally don't have class at this time, so yeah. I forgot to let my friends, my coworkers know. My bad. They'll figure it out. Okay, so the initial concentration and, sorry, of the reactant, and the rate constant both affect the half-life. Okay, so if they ask you any question, is the half-life, now of course the context here is zero order. I'm trying to think about every angle as I'm talking to you guys, right? So if they ask you, is the half-life of the zero order reaction influenced by the rate constant? You look at this equation. Is the constant K there? Yes. Is the half-life of the zero order reaction influenced by the initial concentration of the reactant? Yes. Why? Because this symbol means initial concentration of the reactant. In other words, are those symbols in the formula? Yes. Okay, so that's kind of how they ask it conceptually in words. Okay, I won't do this much talking for the second and third part because it's going to be the same trend, just applied to different orders of the reaction. So hopefully that makes sense. Okay, so we know this one here. We've seen the graph here. Oh, last thing, we need to get the units, right? We talked about this before, but I want to see how we get the units for K. So we did this before. Units for the constant K. In this context here, we're still in zero order. So in zero order, constant K is, let's see, I'm going to use the half-life to get the constant K. We got it yesterday through different means, right? But I want to kind of remix it today as you can see how these all connect together. There's a lot of math here in 1412, so hopefully you can see that. We're trying to solve for K, right? So I'm going to rearrange this. I'm just going to switch these positions here. So 2K equal A and then 0 T1/2. I guess I can bring this 2 down here. Divide by 2, divide by 2. That gets rid of this right here. Okay, this is what I'm dealing with. Now I'm going to replace the units for A. A is a concentration, right? Because it has the brackets. So this part here is a concentration. Units are molar. Okay? And then T1/2. Okay, this is the concentration. The concentration units, the universal symbol is molar. So molar. The bottom unit is a half-life. Half-life is a time, and the unit here is seconds. So it's molar per second. So the constant has this unit, molar per second, or it's written as molar per second. We talked about this yesterday, but we started off with a different path, but we're ending up with the same constant. Okay? So I don't know what this triangle is. This is a formatting issue they had when they were working out the accessibility thing. But yeah, so you see how I derived that. Like I said, with the other ones, I'll go a little faster. But yeah, that's the first one. Now we're moving on to the second scenario, which is the first order. Zero order done. Now we're dealing with the first order. With the first order, once again, focusing only on the reactant. A is a generic reactant. We don't know what it is yet. It hasn't been defined. Let me add a page here. So with this one here, we're starting with a rate law. This is all about first order. So the rate law is rate equal constant raised to the power of the reactant. Sorry, it's constant times reactant, right? Raised to the power of 1 because it's first order. Okay, so the 1 is implied, we leave it out. Then after integrating this, you integrate. Now when you integrate this, you end up with the log natural of the first scenario. So you see here, at first for the zero order, we had A concentration sub T equal negative K T plus A sub naught, right? When you put in the log natural here and the log natural here, ta-da, you get the first order. So this is the first order in linear form. But this time, the difference is you have log naturals of the amount of the A, the reactant left over, right? Okay. So like I said before, you want to know this equation. This is the integrated rate law. We know the purpose of it. This goes with first order only. Doesn't work for the other ones. Okay? Now you want to know this in the point slope form. So in the point slope form, how does this work? This is going to be your y equal mx plus b. So just like before, we'll draw a graph. This is going to be your x label. This will be your y label. This will be your b label, which is a y-intercept. Now let me look at the symbol on the slope. The slope is negative, so just like before, right? You have your y, you have your x. What's my y again? ln of A versus T. Okay, so my y is going to be labeled ln of A. My x is going to be labeled T. I'm just going with this right here. Okay, you can just say like that. That works too. Okay, so whatever y is, you label that. I know it's linear because remember I told you these equations are linear. So it's going to be a line, but since there's a negative here, it has to slope backwards like that. And then for my slope here, my slope is equal to negative k. So my slope here will be equal to negative k. Oh, I forgot one more thing. I have to label my y-intercept. My y-intercept, this point right here, is log natural A sub 0, because it has to match this one here, right? Log natural A sub 0. This is essentially the initial concentration, initial because time is 0. When you take the log natural of it, that's what this number is. Okay? So hopefully you're getting the hang of how I'm drawing the graphs. You want to be able to not only draw the graph, identify the graph. Okay? Oh, now we're going to the constant. So see, we've done the graph. This part is done. Slope, I did all the part. Now we're going to the constant, the rate constant. Okay, we have to do the half-life first, though, before we do the rate constant. So I'm going to go to the half-life and do the rate constant, and then we'll go through the slides, okay? So back here, let me add a page to be consistent. Half-life. Just like before, with the half-life, we're replacing two parts. We're replacing the time. So here, once again, replace T and this one here. And then once you replace it, replace T with T1 half, this with A over 2, and you work it out, you actually end up with half-life equal log natural of 2 over K. This is commonly written as the half-life equal 0.693 over K. So I'll say know this. Remember, this only works for first order. Okay? You want to know the half-life equation. Now you can see there is only one thing that influences the half-life, right? So here, only the rate constant influences the half-life. Since K is constant, comma, you can say the half-life, T1 half, is constant, right? Because the number 0.693 is 0.693 all the time, and K is constant. So a number that's not changing, aka a constant number, divided by a constant number will produce a constant number. So T1 half for first order is constant. Okay, so you see how they take a simple equation and derive so much from it. People tell me, you're overthinking stuff. I'm like, that's how we get trained in chemistry. You don't just look at an equation and move on. You get so much stuff from it, right? So in this equation, only the rate constant K influences the half-life, but since K is constant, you can say T1 half is constant, okay? So remember this equation, simple equation. The other thing now we're going to be looking at is unit of K. Okay, we know that T1 half is equal to 0.693 over K. So if you're trying to get K, you switch these positions here, right? So K becomes equal to 0.693 over T1 half. We're trying to get the unit of K. Well, this number is unitless. There's no unit. T1 half is the time. So the unit for this is seconds. Therefore, let me add a page here. Therefore, K, just by units alone, is 1 over second, because there's no unit on top, so just leave the number 1. Then on the bottom, you put the unit, right? Second. So this will be like that, or per second. Okay? So hopefully you're getting the hang of this kind of thinking. If it's not flowing with your mind, don't worry. Keep watching it. I'm currently on the side, for personal interest, learning stuff about finances, because finances has a slightly different logic from science, but it's similar. You use graphs, you relate equations, you look at trends, kind of stuff I like to do on the side. Anyway, so some things I can't learn, I get so frustrated. But then what I do is I just throw myself into it, watch videos about it, work things out, and then before you know it, my mind begins to make the connections quicker and quicker, and then it flows a lot easier. So if it's not flowing at first, work at it, and your mind will start to form connections, and it will become a lot easier for this to connect in your mind, okay? Don't give up, just work at it like I'm doing. Okay, so we've seen how the rate constant is now per second, or remember this is 1 over second. You have your graph right here, so yeah. We already went over all this part here, so I can move on. See? Okay, so this is one of those picture questions where the pictures communicate a lot. So what we're trying to see is we want to spend some quality time looking at half-life of the first order. So let me give you guys kind of like a tidbit about the future. We spend a little extra time examining the half-life of a first order reaction Okay, because when I was in school, I always had these deep questions about, well, why? Okay, to me they were deep, right? I mean, I get that we are learning it, but in my head, zero order is equal to one, first order equals to second order. Why do we spend all this extra time on the half-life of just the first order? Why didn't we do that with a zero order? Let me tell you why, okay? If you're anything like me, towards the end of this class, we'll talk about nuclear chemistry and nuclear reactions. In the nuclear reactions operate via first order. Okay, so in the grand scheme of things, this becomes more popular because we see it again in nuclear reactions. So we're spending more time not right now because we're also prepping for a future when we get to nuclear reactions. Okay, so hopefully you understand why we're spending a little extra time on the first order reactions. It tends to be the more popular of the three. Okay, because I was just like, why? I really don't think I was that annoying, you know. I mean, in my opinion, that's my teachers. They gave me the look, and I gave them the look. We had this understanding. I mean, all I can say is they still like me. We're in contact. I work with them, so I think it worked. No comment. Anyway, this is a graph that shows you half-life for a first order reaction. So remember I mentioned that the half-life T1 half, which is a half-life of a first order, is constant. Okay, so what this picture is doing is illustrating two things, in my opinion. First of all, it's showing you that it's not a picture, sorry, a reaction can have more than one half-life based on the definition. So let me see. I'm trying to write stuff here. I feel like I need more space. I don't want to add a page because I want to write it around here. So two objectives in the picture. Number one, reaction, besides the one about the nuclear reaction in the future, right? Reactions can have more than one half life based on what the definition of half life is. Number two, oh, half life in first order is constant. Okay. Okay, so let's see how this is illustrated. Now with this one here, what I'm going to do, I'm not going to count this one. Listen. I told my other class I got counting down. That wasn't the truth. Counting is a chore. Okay, we'll count. So when you have a picture like this, I usually suggest, if you're not sure what's going on, count the little atoms they gave you, right? The little circles, the molecules. So we'll go ahead and count, right? Because it's saying here, at time is 0. This is essentially the beginning, initial. And then somehow this picture here showing you the amount of chemicals left after one half-life. So let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Made it. Okay, so in the beginning, we have 24 amounts, whatever that is. Okay, moles. I don't know the units, so I just say 24 amounts. After the first half-life is the time that has to pass for the original concentration to be halved. So we have half of what we started off with. Let's see. 1, 2, 3, 4, 5. Ooh. I'm a little lopsided here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, look at that. 12. 12 is half of the original amount. So the time it took us to go from 0 time to 100 seconds. Oh, it took 100 seconds to go from 24 to 12. So our first half-life here is 100 seconds. Since this is for a first order reaction and the half-life is constant, you see, this is how stereotypes happen. Well, we don't call these stereotypes. This is how predictions happen in science. Since they said the half-life is a constant number, that means if it takes 100 seconds to get to half of the original amount, guess what happens in the next 100 seconds? we see another half-life. So 100 seconds passes. Bam. And then now this becomes the new starting point for our second half-life. So now we see one, two, three, four, five, six. Hey, isn't six half of this second starting point? And then another 100 seconds. Bam, right here. Now, with this as our new starting point, we end up with half of this new starting point. One, two, three. So then you can say, in this overall process for 300 seconds, we went to three cycles, right? Three half-lives. So that's how you interpret this graph. This graph used to make me nervous when I was in school. Can you imagine that? It's just, everything made me nervous. If it was new, it was both exciting and nerve-wracking. Because I'm like, ooh, new information. And I was like, But then I enjoyed the challenge, That's why I stuck with it. Plus, it was my major. Oh my goodness. Okay. I did really enjoy the challenge. I could have picked something else, but I enjoyed the challenge. So here we're actually working out a problem. This will be a conceptual kind of problem, right? Here we're working a mathematical one. It says determine the half-life for a first order reaction. First order. That is K. Oh, half-life, right? So it's the other way around. T1 half equal 0.693 over K. That's our equation, right? Determine the half-life for the first order molecular iodine dissociating at 625 Kelvin. Okay, let me tell you what happens, okay? This K here stands for constant. The thing in chemistry is you have to, even though they don't emphasize this, I'm just telling you, you have to learn what the symbols are, okay? I know they have worked it out here, but I'm still going to work it out. 0.693 over K. And this K here stands for the constant, right? Not the temperature. I have seen some, I won't mention who because I've forgotten who the people are, who will see 625K and then just place 0.693 over 625K. After all, K goes to K, right? Don't do that. Your mind will play your mind will play tricks on you if you haven't spent the time to really make sure you give your mind boundaries. If you know what I'm saying, right? You want to study because you're trying to make sure if your mind is a connecting mind, it will connect things incorrectly if you're not quote unquote training it right. You train it right by studying to give it boundaries, right? To not make the wrong connections. So here, I've seen people do 625 and then put that here because K matches with K. And I'm like, yeah, but this K was never a temperature. It was a reaction constant or a rate constant, right? So don't put this here. What goes here is this. Plus, you're looking for time. Time should be in a time unit. So let's say you messed around, right? Low key in your heart, you are that person. Own it, okay? If you put this here, 625, and you work it out, you use your units, you end up with a time value of some number per Kelvin. Then you ask yourself, wait a minute, since time is not measured in Kelvin, right? So I did something wrong. Then you laugh at yourself. Go ahead and laugh at yourself. It's okay. Then you're like, no, she said don't do this. Put the time here because time is measured in seconds, right? I mean, I mention this every year, and every year somebody still manages to do it. So I don't know what's going on there. But yeah. So our constant is like this. Now, when they write it like this, I like to write it in fractional form, which is 1 over seconds, right? The denominator of a denominator ends up being a numerator. So when we work this out, the second will end up on top. Okay, let's see. 0.693 divided by 0.271. Ta-da, we get 2.56 seconds. Okay, units help you. I went from hating, when my teacher told me, use your units, I was like, oh. I was a teenager. I had a little bit sass. And then I realized, wait a minute, units help me know I'm going to the right direction. They're kind of like my GPS in dimension analysis. So I was like, no, units are my friend. So yeah, there was some growth there. So even if you place the wrong number there, if the unit doesn't work out, you have to start over. You use the wrong number, right? So you want to use the units because they act like a GPS to kind of help you to the right position or location, so to say. Okay, we're moving on and practicing this problem here. First order integrated rate law and concentration determination. So here we're told the decomposition of SO2CO2 is first order. Now we know what to do. First order, I'll write my log natural equation. So I don't forget a T equal negative K T plus ln A 0, right? This is just like the first one, only I have to put in some ln's here. Okay, so that's where I am. And has a rate constant. So that's K of 2.90 times 10 power negative 4 per second. That's consistent with first order, right? They have this kind of unit. Initial concentration of SO2Cl2. Initial concentration has this symbol, right? Is this number here, 0.02255 m. What is the concentration of SO2CO2? We're trying to find this here. What's left over after 865 seconds? Let me squeeze this right here. Time is 865 seconds. So before I continue here, right, because I know they're going to be working their own thing. I'm going to work my own thing, my own page here. We want to make sure dimension analysis requirements are fulfilled. So you want to make sure that seconds here match seconds here, right? If they don't match, convert them to a unit that you're comfortable with. If you like seconds, go with seconds. Okay? Okay, there, those two. If they match, you can go ahead and plug them in. So what are we solving for again? Oh, we're solving for this part here. Since we're solving for this part, I will leave it till the end, right? So for right now, what I'm going to do, I'm going to write the whole equation. Can I be lazy and copy this over? Let me see. Okay, I'll just copy it over. I shouldn't use the term lazy. My other class says efficient. Let me use them. They're the engineers. I should be efficient, right? And move this over. Okay. So where was I? I have this number. I have this number. I have that number. Oh, I can do this. So log natural A T equal negative K, negative of this number here, 2.90 times 10 power negative 4, 1 over S times, you know what? Hold on a second. Let me do a rewind real quick. I don't want to write smaller. So what I'm going to do is I'm going to do these part by part. I'll do this part first. I'll do this part second. Then I'll combine them in here because I don't want to make my handwriting any more smaller. Okay. So for my negative K times C, I'm going to work it out here. Because I'm looking at this thing. I'm already running out of space. I'm trying to show you all how to do the dimension analysis. 1 over second, right? Times my time here is 865 seconds. So I have ample space. So when I multiply these two, this is the number I get. I'm going to plug the numbers back in the end. Negative 2. Oh, I forgot to use parentheses. Okay. Negative 2.90 exponent. Where's the exponent button? Why is it so dark in here? That's what I said in my other class. And then I still haven't turned on the light. Times 865. 865. Jeez, delete. Okay, so these two give me negative 0.25. I'll say 1. Okay, that's this number right here. So this part is done. Now I'm going to do this part here. Log natural of A naught. And that will be, what's A naught? 0.02255. So 0.022. Oh, I have to do the log natural. Log natural of 0.02255, right? Yeah. So when I work this out, where's my log natural? Second button, the other button, 1, 0.02255, close parentheses, and I get this as negative 3.792. Okay, so since I have these two numbers here and here, these are going to replace this and this, right? So I can now rewrite this. Ln of A sub t equal negative 0.251. The unit dropped off, plus this number here, negative 3.792. This is where I am right now. So I add these two numbers and I get this bottom number plus this top number. I end up with negative 4.04 ln of A sub t. They want us to figure out how much is left over. So how much is A sub t? Okay, so A sub t is going to be, you take the inverse of ln, which is E. So E power negative 4.04, right? Oh, I have to keep reminding myself, where is E? This is the issue with buying cheap calculators, y'all. I just have to embrace it. All these log natural functions for me are second. They're not like on the first, on the little button. I have to go behind, find math, do whatever. I just have to make peace with it, then find it too. Okay, I found it. E power, my answer there. Okay, so after I plug this in the calculator, make sure you do this right. You end up with 0.0175 molar. So what we are saying is, if you were on the phone trying to describe this process to somebody, you won't say line by line, right? So the reaction started off with SO2CO2 being this amount here, the 0.02255. And then 865 seconds pass. Based on this rate constant, this is the amount we have left over, 0.0175 molar. So let's see if that's what they got. They do all that stuff. Yeah, their process seemed to be a little bit shorter than mine, right? Because they had more room and it's a computer typing. I wanted to type big. So here is the things you want to watch out for. If you forget this negative, this number will be very big. Just, clerical error or transcribing error. This number will be very big. The amount left has to be less. So amount left over has to be less than original, right? So if you somehow have more than the original, troubleshoot, you forgot the negative. Then go back and plug in the negative, and then, you should get your answer. In the multiple choice exam, guess what they have? They have an answer choice where somebody forgot the negative deliberately, because they're not just testing your chemistry skills, they're testing your paying attention skills, your math skills, and all the skills you can think of. Yeah. So second order, right? It's like we forgot second order. No, we have not forgotten second order. With second order, like we did before, let me see. No, this is not right. This is supposed to be positive. So let me work out my own, because they have a typo here. With second order here, we're working on second order. I feel like second order doesn't get a lot of attention, but that's okay. You start off with rate equal K, and then you have the reactant, or the reactant is A. We're sticking with A as a format, raised to the power 2. This makes it second order, right? Second order. You do the integration of both sides, and then I'm going to start with the first, because this is how I memorized it, because I told you guys I don't memorize like normal people memorize. I memorize differently. Uniquely, I start writing the first one that I memorized, which is the first, like this, equal negative KT plus A sub 0. Okay? In the second order, though, this is now the inverse. Remember the first order, we put the ln here and the ln here. To get the second order, You make this 1 over what I wrote here. 1 over this. So this is how I memorized it. And then the slope is actually positive. That's why I told you guys they made an error there. The slope here is positive. Only the second order linear form has the positive slope. So I'm going to erase that because positive is usually implied. Okay. So just like before, you want to make sure you know this. So you guys saw how I recreated it. I call that, yeah, unique way of memorizing. So I really learned the first one and then I learned how the second one relates to the first one. Yeah. This is what works for me, y'all. So when we have this right here, make sure you know this. Next thing is, how do you get the linear form from here? Okay. Y equal mx plus b, right? Just like we did before, same thing. Your y will be labeled this. Your x will be labeled this. This will be your b, your y-intercept. This right here will be your slope. Okay. So as usual, we know it's a linear graph. We're getting used to it now, right? Your x-axis is going to be labeled this, t. Your y-axis is going to be labeled that. So you label it 1 over a sub t. So this is check, this is check. Now we have to draw our line. So this is I almost actually speak it out so I remember. This is a positive slope. It's going to be like this. It does have a y-intercept, so I cannot take it right to 0, right? Because it's an actual value here. My y-intercept, which is b, is going to be this number right here. 1 over a 0. So this is going to be 1 over a 0. So I'm done with this part. And then finally my slope. My slope from here will be equal to k. Oh, I forgot to title this. 1 over a sub t versus t. Okay? So you can see how we're kind of remixing a lot of things. We're seeing the lesson in graphing, linear graphs, whatever, relating the graph to the equation, the negative slope, the implication, all that stuff together in one, right? All those low-key learning goals in chemistry. You can see that right there. Oh, I forgot these two. Okay, I'm so proud of myself. Okay, this right here. Next thing we're doing here, oh, I want to do it above, right below the other one. So let me add the page right here, is half-life. So the half-life of this one here, okay, the half-life of this, oh, I wrote a lot on that one. 1 over a sub t equal kt plus 1 over a sub 0. The half-life of second order, as before, you're replacing this, right? And this, the half-life is going to be equal to 1 over k and a, right? That's what I got, 1 over ka. Yeah, 1 over k times the initial concentration of a. So here's one of those statements again. Half-life of second order depends on constant and concentration. I should say initial concentration. Initial concentration of reactant. Okay? So remember, all I did was just describe this equation in words, because when it took me a while to realize the conceptual parts in chemistry, they're just saying the stuff that's in equation and calculation form in words. So you want to get the hang of that so that you know, right? So half-life of second order depends on constant and the initial concentration. They'll rarely ask you about the constant, but most of the time the questions will ask you about initial concentration of the reactant. So they can ask you, does the half-life of the second order reaction depend on the initial concentration of the reactant? Of course, your answer is like, yes. I'm about to say duh. You can't say duh. Yes. Yeah, the answer choices will be yes. Okay. So yeah, the units for K. Listen, this is my job, so I try to make it interesting because every semester I'm back here, right? Every time I teach 14, 12, I'm back here teaching this stuff. If I don't make it interesting for me, my brain just gets bored and shuts off. It's like, okay. So I have to make it interesting. So if I sound like I'm having a little bit too much fun, I really am. It's kind of necessary. So we're trying to figure out what K is, right? The units for K. We figured it out before, but we had a different starting point. Now we're trying to rearrange this. So starting with T1 half equal 1 over K sub, yeah, K times A, which is essentially the initial concentration of A, because you have the concentration brackets and then the 0, which is not, and that means the beginning. Okay. Remember, starting with this, we're trying to get K by itself. So what we're going to do is multiply, let's see. I'll be lazy about this. Let's switch this around, right? Switch these two. So I'll do K times A sub naught equal 1 over T1 half. And I'm trying to get K by itself. Divide by A naught, and then divide by, I can just put this underneath here, A naught. And then that works out. So we end up with K being equal to 1 over T1 half times A naught. Okay, naught just means 0 or the initial. Okay, remember this is a time measurement, a specific time, but time nonetheless, so this is second. This is a concentration, so the unit is M. So replacing the symbols with a unit, we end up with 1 SM, which is probably written as 1 over MS, which is the same thing as K. If you want to bring the M and the S up, mathematically it becomes M power negative 1, S power negative 1. So they're notorious for using either one. When I was in school, I didn't like the variation so much. When I'm learning stuff, I like to learn it one way. Then when I'm feeling a little comfortable, I can kind of switch it up. But the teacher or the author is already switching it up, and I'm like, but I'm still trying to get comfortable with this. So what I do is I low-key just anchor with one. So when I was in school, I became comfortable with this one here, but I knew the mathematical conversion. So I was comfortable with this one and used that as my anchor of understanding. And then when I saw this, even though the teacher was communicating this, in my head, I flipped it back to this because I was just more comfortable with this. And that helped me to logically continue with the lesson. And then later on, by junior level, I was like, oh, I can do either. Now I'm fine with either, right? It's just I got to a point of realizing that I am who I am, and chemistry is what it is, and we have to find a happy medium, right? So I'm like, I prefer this, but the teacher is switching between these two. So I picked the one I prefer, but mathematically, I know this can flip into that. And then as I got more comfortable, I was more ready to embrace this form here by junior level. But junior level chemistry is the same stuff, just they throw in some calculus in there, right? So you see that here. So you see, I will look at this and then I'll write it as well. This is how it really is in my heart, in my preference. We saw all of this already, right? And at some point here, we should have the summary table. Oh, there it is. So yesterday, I showed you this part, and I said we went over this order of reaction, 0, 1, 2, rate. We went over that. And today, we got to see how this relates to this. Oh, they got this form right over here. So you see, this table here summarizes a lot of things. It shows you the order of reaction, what they call the differential rate law, differential. I rarely see this term, but sometimes when you, depending on the level of the author, sometimes, especially people who are doing research, they tend to use more high-level language. So they're talking about differential rate law, and you're thinking, wait, I only know of a rate law, but all they mean is the regular kind, this one here. Then the integrated rate law is the one that they have integrated from the differential form, okay, which is this one here. So the differential rate law is the regular rate law. So depending on the resource you're getting your information from, That's pretty much it. You have your graphs right here. You have your half-life expressions and then your value of K here. Okay? To summarize everything. Okay. We're not doing that bad as far as time is concerned. So now we're kind of, after doing a little bit of that math and discovering things, we're now moving on to the details, right? You thought that was the details. Now we're looking at kind of the play by play. Remember the relay race? We're now looking at reactions within reactions that influence the overall rate of the reaction. So before we get into that, we have to talk about activation energy. Usually here I talk about the definition essentially says is the minimum amount of energy that reactants must have for the reaction to take place. It's kind of like a prerequisite, okay? So activation energy is a prerequisite energy. Okay. So one of the educationese languages that I've heard is the threshold. At first I was like, threshold of what? It's a threshold. And you're like, yeah, you have no idea what it is. So, okay, so sometimes instead of using the word prerequisite, they use the term threshold, right? So that's like the minimum requirement. Okay, so sometimes they'll say threshold energy, the minimum requirement that the reactants have to get to in order for the reaction to take place. So it's kind of like a standard, right? And that's the activation energy. Sometimes it's called an activation energy barrier. Okay. Once again, just to say that if reactants don't get to this energy, the reaction is not taking place. Yeah, it says so right here. So think about it. It took me a while to kind of understand this picture because I don't play golf. But for the same picture, I just put myself in here. Remember I told you guys I like to put myself in here? I used to run cross country. Never said I was good, but I used to consistently run. Okay? So I didn't really get the golf analogy at first because as soon as I saw the picture, all I could see is myself running hills. So when we used to run cross country, one of the things you had to be able to accomplish was running over a hill. Okay. So you try to conserve your energy when you were doing flat stuff, but when you got to near the hill, the goal was for you to muster all the energy you had to run up the hill, put all the effort, get to the hilltop. Once you get there, you kind of coast to the bottom of the hill. You don't want to run too fast because you fall over. But the idea was it was considered that if you just got to the top of the hill, you pretty much made it down because this was where the work was, right? And then this one here, you're just coasting all the way to the bottom. So the activation energy barrier is essentially a standard, right, that these reactant molecules have to achieve. The reactant molecules have to absorb energy, get up here. If they get up here and they don't make it to the top, they fall right back down. Such is life. Only the higher energy ones react. The molecules have to gain enough energy, get to the top, and then once they get here, the chances of them reacting is very high. They have met that threshold. So the idea here, the ball has to get here. Once it gets here, it can easily go over here. Doesn't mean you'll go here, but it can easily, go to this side. Okay. So at some point, we're told that we mentioned this in the beginning. Apparently, temperature affects the rate. Okay. Now, you would think the effect of temperature on the reaction is some neat linear relationship, right? Why does it have to be this complicated? This is what Arrhenius. So we talked about Arrhenius in 1411, talking about acids and base, Arrhenius definition. So Arrhenius, a scientist, studied the effect of temperature on how fast a reaction goes. And this is the relationship he found. A complex relationship. I mean, in real life, this is how it plays out. You heat a sample as it's reacting, the reaction goes faster, right? It takes less time. But when it comes to the relationship, this is the equation we get, okay? So don't panic about the equation because I told you guys that chemists have a knack for linearizing everything they can linearize because it makes it easier for them, and I am very grateful for that attitude. But essentially, I want to rewrite this. This is the reaction constant that we're used to, the rate constant, equal to And then A is the frequency factor, and we'll talk about that, times E, the log natural E, raised to the power activation energy over RT. So this is what the equation really looks like. So here we have K. K is that rate constant we're looking at before. So this is the rate constant here. And I just tell you, this takes the place of rate. So there isn't a direct relationship between temperature and rate. There's a direct relationship between temperature and the rate constant. And I'm like, yet in the beaker, it looks so simple. In the lab, it's like you just heat up the reaction to make it go fast. But in the theory of it and the mechanism of it is complex. The temperature is all the way over here. And what it's influencing in the end is this all the way over here, right? It's not a linear relationship. Now we'll linearize it, but from here, it's not a linear relationship. Okay, so we got rate constant. So think of rate constant like we thought of rate, okay? How fast the reaction is going. So that's what it's telling us. And then we have, I guess I'll go in order. A is the frequency factor. The frequency factor, I would say, relates to number of collisions. So for the most part, when we're working on this in lab, we don't even try to solve for this because we don't have a mechanism or a way to measure the number of collisions of the molecules, right? Most of our instrument in the lab is very simple. Okay, of course, E is log natural, so I won't even define that. EA, that's the activation energy barrier. That's the requirement that the energy have to, the molecules, sorry, the energy requirement the molecules have to reach in order for the reaction to happen, right? That's activation energy. So I've done this, I've done this, I've done this. And then, of course, R is the gas constant. So for this one here, because activation energy is an energy in joules. Actually, at some point, they haven't shown it yet, but it'll be an energy in kilojoules. Because it's of this joules here, you have to use an R that's 8.314 joules per mole K so that these can map out to each other. You can't use the other one because that one goes with gas and atmospheres and stuff like that. This context here is not even about gases, okay? So let's see, define R, and then T, of course, T is that temperature we're trying to increase. So temperature of the reaction in Kelvin, right? Yeah, so temperature in Kelvin, because once again, it has to map up to this bottom part here. They have to match. This has to match that. So there's all these dimension analysis requirement going on. So you want to be aware of this exponential relationship between temperature and how fast the reaction goes, right? Which it's harder for us humans to really relate to that and chemists. So what we do is, in the place of this, we integrate. So to change an exponential relationship to a linear form, we integrate this. So let me show you what it looks like when you integrate it. Integrate. We integrate this equation to get a linear form. So let me fast forward so y'all can see. We haven't gotten to it yet. We'll get to it. Oh, there it is. Finally. Here is the linear form. Okay, so I'm going to bring this back here so you can see. All of a sudden, integration was looking so great. And even though we haven't gotten to that part yet, this is a more usable form for us, right? It's a more usable form. So we take that equation, we integrate it into this form right here. And then after we integrate it into this form, now we have a linear form, which is a point slope form. Remember the y equal mx plus b like we saw before? Okay, so I'm going to come back to this middle part, but I'm going to skip over this part so I can, because I feel like this ties into better. And then, of course, I'll bring in the point slope form down here because they kind of flow into each other a lot better versus the way the slides are organized. Okay, let me add a page here. So from here, I'm going to show you the graph and I'll show you the point slope form. So once we have this more usable form, this is the integrated version. Once again, integrated version of the original equation. I'll say this is a more usable form. Now from this version here, we can draw a graph again, right? Like we did before. This would be our Y label. This would be our X label, right? And then this would be our Y-intercept label. So I'm going to draw the graph here because it's one of those learning requirements. Y versus X. My X is 1 over T. My Y is ln of K. Right, so I've done this part, I've done this part. And then I have a line, because this is a linear version. My line has a slope, and it's negative. So I'll just draw my line this way. I forgot to title it. I'll do that in the end. Okay, my slope, oops, I just call this slope, has to match this right here. My slope is going to be equal to negative EA over R. Okay, so I've done this part, I've done this part, I've done this part. I need to put my B. B is always where the line crosses the y-axis. So this is going to be log natural of A. So now I've labeled this. Okay, one more thing. Oh, I guess I should put this over here, right? ln of A. One more thing. Title. The graph has to have a title. Oops, I didn't mean to do that. The title of the graph is ln of K. Wait, why are these symbols different? This should, oh yeah, I'll talk about that in a second. This should be ln of K versus 1 over T. I was jumping ahead of myself, right? So you're drawing this according to the equation. Yes, that's true. That's the equation right here. This equation, once again, is useful for drawing graphs. And of course, is useful for determining the linear relationship. So for drawing graphs and linear relationship. Okay. So remember how I was saying y is ln of A here? Because this is what happens. In real life, like I told you guys, we don't have a device in lab to figure out what A is. Technically, we can use K and T to figure out what A is. Once we draw the graph, whatever comes out here, we can solve for A. But it's a more complex way. So the easiest way, y'all, chemists do a lot to make life easy for them. They do a lot. Okay. The easiest way for us to kind of solve this and leave A out of it is to use two experiment conditions so that A is not considered. So what I mean by that is when you use two experimental conditions, this equation here, when you mathematically work it out, ends up being like this. So I am not actually going to mathematically work this out because that part is not a learning goal of this class. If you minor in chemistry, you will be required to work it all out. I don't really have a lot of time to go into that. But for two experimental conditions, that means two temperatures, T1 and T2, two rate constants, K1 and K2, you end up with this right here. You see how the log natural of A got left out because it works out that way mathematically, okay? So this equation will actually be log natural K2, please realize there's a parenthesis here, over K1 is equal to EA over R, and then we have 1 T1 minus 1 over T2. Make sure the units are working out correctly. This is K in Kelvin. This is K in Kelvin. This is the constant I was talking about, 8.314 joules per mole K. And then everything else works out mathematically. Okay. So that kind of shows you how we go from here, right, the effective temperature, all the way to That equation right there. So this equation will help us solve for either activation energy of a reaction, so we can figure out what the number is or what the constant is here and here. I'm trying to figure out how to end this lesson. So what I'm going to do here is, let me make some modifications here. This will make my life somewhat easier. Yeah, I'm going to actually work out this problem here. So I don't get confused when I come back to this next week, I will go from, yeah, I'll just go to here. So let me see if I can copy these pages. I don't usually modify these slides, but let's see. Select that, select that, select this. No, can I double select? No, snap. Okay, this is what I get for being, can I move this? Okay, just copy. I'll copy and paste this here. So it's consistent with what I just went over. I have to add a page. Yeah, I usually figure all of this out before I meet with you guys, but since what is it called? I'm kind of improvising. Just bear with me. Okay, I can delete this page here. That goes over there. I want to copy all the pages I already discussed, so they go together. So when you guys are working on this, it's not complicated. Okay, so I can cut this page now and put it over here. I think I know what I'm doing. Paste. Okay, it went over there. And I can cut this next page over here and then paste. This is fun stuff. Paste. Right? And I can cut this next page. Oh my goodness. Almost done, almost done. Here. Just a couple more. Cut. Because I want to finish that thought, and then that way I'll end it. Then when we meet next time, I'll just finish this last part that has to do with reaction mechanism. So the thought is the same, right? Come on. Did I press paste? Okay. And then let's see. So this is all the gibberish stuff they have. It's supposed to be work. Cut. When I actually look at it, I'll remove all the duplicates. Paste. Okay, then finally, I think I see one more. Cut. Okay, and then paste. Okay, so this is where we ended, right here. After I showed you how this equation is used, so we are right here. And I showed you the modified equation, the one that we use to actually solve for things. Okay, so here I just went over that, the Arrhenius plot, and what this is for. This shows you algebraically the relationship between temperature, right here, and the rate. This is the rate constant, but we see it as a placeholder for the rate because the rate could not make it here, like the sub for rate. And then we go into all of this, and then the next thing we do here is show you the graph and that. Wait, this is to duplicate. Oh, okay, my bad. I can duplicate that. Delete page. Okay. Then here's where we have the point slope form. This was done to eliminate frequency factor since we don't really want to figure that out. And this is where we're able to use two different experimental conditions to solve for activation energy as needed. Okay. Then finally we have a problem here, and then we can work this out. A lot of gibberish, and then we get the answer. Okay. So here we're good. So I'm going to work this out, and then this is where we're going to be ending for today because I feel like I've said a lot, right? Okay. So now that we have the point slope form of the equation, we're going to be using that to solve the problem here. So I'm just going to copy this onto a page. The page will be like right here. That's the equation we're going to be using. So for this, I need the information. It says, consider the reaction between nitrogen dioxide and carbon monoxide. Yep, these two. The rate constant at 701 Kelvin is measured as, the units is messed up here. Okay, So we're given the rate constant, the first rate constant, K1, as 2.57 per meters per second. So you can say m power -1, s power -1, right? And I have a temperature that goes with that. That is 701 K. So I have this number here and that number. And at temperature 2, 895 K, I got this temperature. You have the second constant, K2, which is 576 m power -1, s power -1. The little g in here is a typo. I cannot change it because it's an image. When they were trying to make the slides accessible, I think they were typing very fast because we had a federal deadline. So yeah, there's some typos here. Find the activation energy. So solve for EA. Okay, that's the activation energy. Oh, in specific units, make sure they're in kilojoules per mole. Okay, we can do that. Is that it? That's it. Okay, so let's see. Let me write this so that they're kind of more uniform. It's those small things, right? I know you're probably thinking, why does she? I don't know why I do. I just do. Okay, I just do. So I'm gonna move this over. I'm just gonna move this over. It makes me feel better. And when I don't feel better, I obsess over it. I know I have these little obsessive tendencies. Okay. So we have T2 here, T1. Yeah, so all the one information are together. All the two informations are together. So I think I'm happy now. Now, let me see what I'm missing. I'm doing a quick inventory. I have K1, I have K2. I have T1, I have T2. Ooh, I'm missing R. R is 8.314 joules per mole. I'm looking at my units and seeing that joules mole, okay. So what I'm going to do here in my math, I'm going to section this also. I'm not doing too much at once. So what I like to do here, I'll just show you. I like to section the math out. So I'm going to do this part here first. Now do this part here next. And then we'll solve for E. So this is going to be first. This is going to be second. And this part here will be last. Okay? Because we're trying to solve for EA, activation energy. So that has to be last. Okay? Okay. So my first plan is to solve for 1 over, is it T1? Minus 1 over T2. I'm trying to solve this part first. So 1 over, what's T1? 701 Kelvin minus 1 over 895 Kelvin. Okay, I'm going to plug this in my calculator. I guess I can make this slightly smaller, can I? Yeah, okay. Okay, so I got open parentheses, 1 fraction 701 to the right minus 1 fraction 895 to the right, close parentheses. Oh, I get 0.123309215. Okay, yeah, that's what I get. So these are all Kelvin, so this looks like it's going to be Kelvin power -1, right? Or 1 over Kelvin. Yeah, that works. 1 over Kelvin. Because the Kelvin unit is on the bottom, right? So this part is done. This part, done. Next part is this part right here, number 2. Number 2 is finding ln of K2 over K1. And this is going to be in parentheses. So I'm going to set this up here. Where's my K2? 576. 576 m power -1, s power -1. Oh, I forgot my ln. The ln is right here, right? Over K1 is what? 2.57? 2.57 m power -1, s power -1. So let me see. Where's 576? Let me make sure the numbers are right. Yeah, 576.57. Okay. The units, of course, cancel out. I end up with my answer as 576 divided by 2.57 equal, okay. So this is the same thing as ln of 224, which is log natural. Let me go find it. 1, put my answer in the close parentheses, which is 5.41. That's all I'm going to write. Okay, so once I'm done with this, now I can plug this part here and this part back into the equation. So I'm going to write it as 5.41 equal EA over R times 0.000309215 over Kelvin. This number here has no unit, okay? So I'm going to work this out. Of course, divide this number both sides, right? Divide this number both sides. It's a huge number. 0.000309215. 0.000309215. 1 over Kelvin. This cancels out. 1 over Kelvin. Denominator becomes numerator, right? This cancels out completely. So now I have 5.14 divided by that number. I'm not going to type all this out. I'm going to find it in my calculator. Where is it? That number. There. And when I divide this, I get 17503.04. And this becomes Kelvin, right? Because, yeah, it becomes Kelvin, denominator. Then here I have my activation energy, which I'm trying to solve for, over 8.314 joules per mole Kelvin. Okay, so you multiply these two to get activation energy. So essentially 17503.04 Kelvin times, I'll put times here, 8.314 joules per mole Kelvin, right? This is our activation energy. I just multiply those two versus switching them. I'm multiplying. K and K cancel out. I'm already feeling a lot better because my units are joules per mole, which is kind of a step from where I'm trying to go. Joules per mole, yes, I'm feeling excited, times 8.314. Oh, look at that, 14550. Joules per mole is my activation energy, but they said they were very specific. Kilojoules per mole, right? Somewhere I wrote it somewhere here. Oh yeah, kilojoules per mole. Well, we can do that. I just bring this closer. This is joules per mole. This is our activation energy, right? I can write it actually here. So I can convert on the right. Let me convert to get the right unit. To convert this, I put 1 kilojoules and then 1,000 joules, right? Joules. We get kilojoules per mole, which is this number I have in my calculator divided by 1,000. And bam, I have 145.5 kilojoules per mole. Okay, there. So when I was in school, I used to try to work this all out together. I consolidated stuff, and then I'll get confused sometimes. And I decided, there's a more efficient way to do it to where it works. And as a teacher, I think it's a lot easier to sort it out like this. You don't have to do it out this way, but it's just when I'm having to teach, I think it's a lot easier to do it that way, and then plug it back in, rearrange. Okay, so 145. Let's see. They do stuff. They get this. Excuse all the stuff here. It's all about formatting thing that happened, but they get 1.45 kilojoules per mole. I don't know how they messed that up. It shouldn't be 1.45. It should be 145 because you see over here they have 1.45 times 10 power 5. 1, 2, 3, 4, 5. Yeah, joules per mole. This should be, yeah, this answer here is not correct if you started off with this. The decimal should not be here. So it should be 145 kilojoules per mole. Activation energies tend to be higher, like they're usually in the hundreds, the magnitude. Okay, so this is where we're ending today. I know I said a lot. We are a little behind, but I didn't want us to be even more behind than before. So we're not doing that bad. So when we meet next, we'll be talking about the activation energy barrier. Then we'll move into reaction mechanism and deal with the individual ones, and then elementary steps, and then catalysts, and then the end, right? At some point, yeah. Matchmaking, yes. All that stuff in chemistry. So I'm gonna write a note to my future self, which is just me next week after I've gone through the weekend to start here. Um, if you have your lab kit, work on the lab, at least work on collecting the data when it comes to, what did I just press? Start here. When it comes to processing the data and making sense of it, once we go through, I mean, if you're not able to figure it out reading the theory, once we go through the catalyst part, it might make more sense. Okay, but if you work on the lab part, at least get that data ready, then it probably might help you after we go over this next week. Okay. Other than that, this is all I have for today. Thank you very much, Vasia, for showing up. It's I don't know why it is. It's just harder for me to talk to an empty screen. I mean, like when nobody is there, I start doing crazy things, and then it's just there's no stopping me. It's not good, right? When somebody is there, I at least try to act a little civilized. So yeah. So well, thank you for showing up. Have a nice weekend. Okay. Thanks.